Hello and welcome to this video that will investigate how to determine if a rational function has a vertical asymptote. Just some overviews of rational functions. Rational functions, just in the broad strokes, tend to look like fractions that have variables in them, particularly variables in the denominator. They also could have variables in the numerator, but as you see here in these examples, because they are simplistic, we don't. So we're just going to be looking at 4 examples of rational functions that have variable terms in the denominator. Okay, so we're talking about this thing of a vertical asymptote. So what is in fact a vertical asymptote? Well, in short, a vertical asymptote is a vertical line. Okay? It's a vertical line that has special properties. Okay, but if it's a vertical line, it has the equation of x equals some number, where this number is the place of intersection on the x-axis. Okay, so just as a rough sketch, if you had an asymptote at x equals 7, you would have a vertical line that goes through 7. Okay? Okay, so that's the basic notion of what a vertical asymptote is going to be. It's a vertical line, but it's a special vertical line. It's a vertical line that is kind of a boundary for a function or a discontinuity in a function. And you'll understand this more when you get into calculus when we talk about limits. Okay, but something is an asymptote for a function, and I'll say that this x equals 7 is an asymptote for this f of x function I'll draw in red, because as the function approaches the asymptote, the function shoots off to either positive infinity or negative infinity. Okay? So I could have actually drawn this function a couple of different ways, because we could have had it so that it shoots off to positive infinity from both sides of the asymptote, negative infinity from both sides of the asymptote, or I in fact could have reversed this and said from the left side it shoots off to negative infinity, and from the right side it shoots off to positive infinity. Okay? So this is the phenomenon of an asymptote. We haven't talked about where to find them yet. We're just kind of talking about what they are. Okay? So in the formal definition is that you have a vertical asymptote at x equals a. Okay? A being this number, okay, in this case it was 7, if and only if the output of the function approaches, sometimes referred to as shoots off to, positive or negative infinity when the input, called x, approaches a. So what I'm saying here is, as I run along the x-axis, I see the function shoots off to infinity as long as I'm approaching this number. So if you see I'm approaching 7 from the right, the function shoots off to negative infinity. As I'm approaching 7 from the left, the function shoots off to positive infinity. Okay? So that's the phenomenon. Okay. Well, how do we find it? That's a little bit different, okay? But you can't lose sight of the fact that the nature of an asymptote, it's not so much about the asymptote itself. It's about how the function acts near the asymptote. That's what's worth studying. Okay, now that being said, finding asymptotes is a lot easier. We talk about where we have discontinuities. Okay, well, in fact, they're going to happen where you have a value of x in the denominator that makes the denominator only equal to 0. Okay? And I'm saying the denominator only for right now because we'll talk about if it's the numerator and the denominator later in another video, which talks about a discontinuity called a hole. So again, an asymptote is a type of discontinuity. and a whole is another, but we're just focusing on asymptotes now. And they are places where the value of x, when used in the denominator, makes the denominator only equal to 0. And we've talked about this in class a little bit. If you have my class, we say the 11th commandment is thou shalt not divide by 0. Well, you get this asymptotic effect when you divide by 0. Okay, so it's decently pretty easy if you think about it. The only thing I need to find out is say, well, when is the denominator equal to 0? And in this first function, g of x equals 3 over x plus 4, it's decently simple. I set x plus 4 equal to 0, and I solve the equation and get x equals negative 4. And again, it's x equals some number. That is the equation of a line, which will be the asymptote of this function. Okay? Don't lose sight of the fact that this part's true. I'll let you investigate that at some other time. If you were just getting close to that value of a, you would in fact shoot off to positive or negative infinity with the output. But let's just examine the graph for a moment. I've loaded all 4 of these equations into the graphing calculator. And if you notice, I'm going to just show you a little trick here. If you go to the equal sign, and hit enter, it'll go from black background to white background. And what that actually does is it turns the graph off. So if you notice now, the only one that has the equal sign bolded is the first one, which is in fact the one I want to talk about graphing. I will hit graph, and you'll see, in fact, at x equals negative 4, I get an asymptote. You can hit trace, negative 4, enter, and you in fact do not get a value for the function because plugging in negative 4 gives you no output, which then also, if you think about domain, the domain is all real numbers except negative 4. Okay, so we'll take a look at the second example where it says y equals negative 4 over x squared minus 9. And again, sort of putting some application to this idea of looking for a value of x that makes the denominator only equal to 0. I will take the denominator and set it equal to 0, and I will solve for x. Now, I could add 9 to both sides and then square root, but I want to just kind of review factoring here a little bit. So you'll see here that I'll take this difference of squares and say that it's x plus 3 in quantity times x minus 3 equal to 0. Therefore, x plus 3 should be 0, and x minus 3 should be 0 by the zero product property, which gives me x equals negative 3 and x equals 3. So we see we have 2 values here, and I'll show the graph for that in just a second. And I want to just kind of focus here on, just sidebar for a second on the idea where we said these are values that make the denominator only 0. Well, they can't make the top 0 because there's nowhere to plug them in because there's no variable. I could have a variable in the numerator, but you know, I try to just excluded that out for this lesson just to focus on basic examples. So I'll go to y equals, and I'll turn off my first graph, which I just did before, and then I'll go to the equal sign here and hit enter and bold it. Okay, and then I'm going to hit graph, and it is not a shock to me that I see 2 asymptotes here. Ironic for me to say I see 2 asymptotes. In fact, I don't see the vertical lines, but I see kind of the places where the vertical lines would be. Okay, so, and I can show them specifically by doing the following. I can show you that the place where when I hit trace 3 gives me no output because 3 is not in the domain of the function. It's where the asymptote is. And if I press negative 3, I would in fact also get no output. If in fact I wanted to draw the asymptotes in, there's a function on your calculator you could do. You don't have to do it. We've said where these values are. The first one was x equals 4, and in this one we say it's x equals negative 4, and then this one it's x equals negative 3 and x equals 3. So I could, however, quit into my home window and then hit second program, which brings up draw, choose 4 for vertical, and say 3. If you notice, it draws in the asymptote. Okay? And then I can do second, quit, second program 4 for vertical and say -3 and do that. And I'll enlarge my screen so you actually can see it here. Okay? And you see, if you can see where I'm tracing through the cursor, is this vertical line is the asymptote, and this vertical line is the asymptote. And again, if you notice, as I'm approaching the asymptote, the output shoots off to -infinity here. Approaching it from this way, the graph shoots off to +infinity there. Okay, so I just took a second to clear that drawing out. Not important how to do that just now. You just clear your calculator if you wanted to. And now I'm going to look at this third example. Okay, so we see we have 5 over x squared plus 5x minus 14. Okay, so what I need to realize is, what is the value of x that makes the denominator equal to 0? So I'll set the denominator equal to 0. And then something very different has to kick in here compared to problem 1. In problem 1, if you notice, it's just solving a linear example, linear equation. So it's just a get the x by itself. Here, it's a little more like this example, and you got to be able to think quadratically, which you would hope it's factored. It's not, so you could use a quadratic formula or try to factor it. Trying to factor it actually goes much quicker. So I'll sit here and say, what are the factors in -14 that add up to 5? So I can use 2 and 7 or 1 and 14 as long as I make the bigger numbers positive. So it looks like 7 and 2 is my winner here. So I'll set up my unfoil type of look, and I will use my -2 and my +7. Therefore, using the zero product property, I have x minus 2 equals 0 and x plus 7 equals 0, showing that x equals 2 and x equals -7 are in fact the values of the asymptotes. These are two equations of two vertical lines. And if I wanted to show that, I could go back to my calculator, turn off this example. Excuse me, I'm in the wrong button. I need to be on the equal sign, hit enter, turn it off, go down one, bold the equal sign there by hitting enter, and then when I graph here, I should be expecting to see an asymptote at x equals 2 and x equals -7. In fact, I do. Verified by hitting trace 2 is getting no output for that input, and again, trace -7, getting no output for that input. Now, again, as these problems grow in complexity, you're going to see that what you need to do in working with the denominator requires more skill. If you notice here, again, this was pretty simple to factor. I'm sorry, this was simple that it didn't require factoring. Then we could have here, like I said, added 9 and square rooted both sides. I wanted to show the factoring option. Here you could have factored even some messier problems where if it can't be factored, you would have to use the quadratic formula. Okay? So this bringing us to our last example, which is a very interesting example. We have here f at x equals 3 over x squared plus 1. So if I have x squared plus 1 equals 0, I would do x squared equals -1 by subtracting 1 from both sides. And then by square rooting both sides, I would get plus or minus the square root of -1, which is an imaginary number, which means there's no real answer, no real x value that makes the denominator 0. That means there's probably no asymptote. So why is this a good example? Because it's an example of a rational function that doesn't have a vertical asymptote. So it lets you to consider this. Do all rational functions have vertical asymptotes? No. But if you have a vertical asymptote, there's a good chance it is a rational function. So I'll go to my graphing calculator, and I will turn off example 3, turn on example 4, and we will expect to see, in fact, no vertical asymptote here. Okay? And in fact, we don't. We don't see a vertical line that creates a discontinuity in this. I'll zoom in just to kind of reiterate it, and you'll see here that there is no vertical line that's going to break the graph. I'll even zoom up a little here. It looks for a second like there is, but I'll change the y max to 6, and you'll see that that is not a break or discontinuity in the function. Okay, so again, what does this mean for vertical asymptotes? Well, in quick review, the vertical asymptote is a line whose equation is x equals number. It's the place where you get a discontinuity in the function, okay? And it really hinges on this definition, which is very important. It's about this idea of approaching a particular input that the output shoots off the positive or minus infinity. Because what's going on with the function is more important to understand than the asymptote, but you need to be able to find the asymptote, okay? So finding the asymptote, finding the asymptote hinges on finding the value of x in the denominator that makes the denominator only equal to 0. And if you're interested in what happens when it makes the numerator and the denominator equal to 0 for that value of x, watch my video on holes. So feel free to watch again. Thanks for watching. Practice, share with your friends, and be well.